Hey, welcome to another episode of Gear Talk and Noria podcast, where we are connecting reliability professionals with reliable information. You know, we talk about reliability, modifying machines and everything, but today we're going to get on the proactive side of reliability, and we're going to be talking with Daniel Rader, and we're going to be talking about how we design reliability into our systems, into our machines. So, Dan, man, I appreciate you coming by and sitting with us. One of the goals of this podcast is for people to understand, you know, more the individual of who's talking. So why don't you kind of give us a rundown of you and, you know, what you're doing and, you know, why you're going to talk to us today.
Absolutely. Daniel Rader, graduated from Oklahoma State University, joined the Navy. Navy's a great opportunity to learn all sorts of things you didn't know were going on in the world. That was where I first got exposed to reliability. You're in the plant, you're trying to keep the steam going, you're trying to keep the ship moving. Hey, this motor's making a weird noise. Oh, did you change the oil? Have you looked at the oil? Have you thought about the oil? It's vibrating funny. Did you do the vibration check? I didn't know any of these things existed. It's not something that they typically cover in a college classroom. Left the Navy, had a chance to continue in that line of work of power plant maintenance here in Oklahoma, and here and there through a couple of other companies have continued in kind of that reliability path. I work for a company now called L3Harris. We're a Department of Defense contractor. It goes back to the Navy. And we're making the equipment now. And so I'm having to think about this in a whole new mindset. I'm not the guy reacting and going, whoever made this thing, I'd be so mad at them. I would have done this. I would have done that. It's like, no, I'm that guy now trying to figure out what we put into it. And so we're considering how long these components should last, will last. We get early reports from our field service reps. These things are breaking, and it seems like there's a pattern. Oh, we gotta go figure out what that is and solve it and make a patch or find a new component to it. And then that goes back to where you were in school, is sitting in the lab with your ohm meter and watching the little sine wave go up and go, yep, try a 50 ohm resistor. No, try a 100 ohm resistor. We're in there just messing until we think the thing stays on. So yeah, it's the same discipline, but man, thinking about it in a whole new way. It's been a fun ride.
Now, we typically think the whole PF curve, right? Mm-hmm. Machines start to fail because of some issue. But I mean, realistically, if we graph this out, we're kind of beyond the y-axis, right? Yeah. We're kind of in the negative side.
Exactly.
Most people think the PF curve starts when the machine is maybe installed, right? Received.
And if we're doing it wrong, we've already sent it to you with the failure, right? Like we're having to really think about, okay, how do we keep it as far away from us as possible? What can we design in or design out, I guess is maybe a better way of saying it, to make it last a lot longer. Some of that is how we test it, you know, up front, getting some field data. And then it turns out there's a whole military standard for trying to figure these things out and saying like, okay, if you have this many resistors, they're all worth this many hours of time.
Okay.
And so then you kind of build and roll up, and you get to do some fun math with some programs. And then it spits out and says, yeah, this thing should last about 800 hours before you have to replace it or really think about it as a failure. And we go, oh, okay. Is that good? I don't know. So it's like, you know, in
what, a little over a month of 24/7.
Maybe, yeah, right. And if you use it less, it lasts longer, you know. And so it's like figuring out, is the number good, right? Just because it is a number doesn't mean it's good or bad. You got to apply it, yeah, how much it runs, and then you got to figure out if it's good. Cool, I want to take credit for it. If it's bad, what do we fix? What was the thing that went wrong? Is it the thing that's the most complex? Is it just one particular item and we could design it out? Maybe we just tested it wrong. We've done that where we proved that we tested it wrong. We tested it too hot in the wrong environment, and it didn't represent what was actually going to occur in the
actual use case, what they're going to be doing.
Yeah, so we changed the parameters of the test. We lowered the temperature a little bit. We changed the pressure that was involved. One of the applications I work on is pretty high up in the atmosphere. We're not as worried about pressure, right? So let's lower it down. We don't need to stick it in like a vacuum area, but like let's try and make it look more like what we're going to use. That improved the life quite a bit. Oh, great. We think we solved it. We think we know what to do now. So yeah, it's thinking. You're not wrong. It's thinking about the curve, but it's like, yeah, how do we deliver it to you? And we didn't accidentally break it before we handed it.
It's not already on the curve. It's still on a flat line at some state. We have high level of performance.
Yeah.
Now, we typically think, we live in a mechanical world mostly at Noria, things moving and everything else, and we don't dive into necessarily all the electrical things. Are you involved in both aspects, maybe a mechanical aspect and electrical aspect?
So the product that I work with the most is a camera system. So the camera's the biggest component of it, but we want to move the camera, we want to turn the camera, we want to point the camera, and so there is the mechanical aspect of it. But your movement is pretty well defined. You're just an inch here, an inch there. Honestly, it's not even an inch, right? Like, you don't have to move a camera very far if you're looking far enough away. And so that's its own problem, is how you control movement that fine. You have to have really precise screws, controls, and so tracking how good those are. Well, great. There's like a company that you can call that makes it the way that you want it, like that. If that company's busted, if you find out from their testing that they're not so good, I mean, you go back to design. You got to start over. We're lucky. We have a couple guys that we really trust, and so we went ahead and said, okay, we know it might fail. Let's buy like twice what we need. Because
we're going to be testing it. We're going to be going through all these iterations.
And then if it does break, and we know failure can be random, right? Let's have one ready to go. Maybe that was just a bad one. So we're definitely looking at mechanical and electrical aspects of it within that motion. We're just not moving as much as a motor or a pump.
Well, sure, right, but I mean, movement still. There's friction involved. Everything else. Now the electrical side, I went through some electrical classes in college as well, and I mean, that's black magic as far as I'm concerned.
Smoke in the box.
Yeah, there you go. You got to keep the smoke on the inside. Yeah. But I remember the oscilloscope, as you're talking about, and everything else. And I guess I don't necessarily think, but I mean, let's call a resistor or a diode. I mean, a diode in a mechanical world would be a check valve.
Yep.
Right. I mean, resistors are, let's call them valves at some point, right? Because they're going to resist different things moving through them. So I mean, there's a mechanical aspect to that because we have energy, so it's going to get hot. All those things are going to deteriorate. So as you're looking through these things, you've got a mathematical, program that goes through this, but you also have to test. I mean, and what do some of these tests, look like? What are the parameters that you're shooting for? What you talked about a camera system, what does that look like?
Yeah. So our camera system, first of all, it looks kind of like R2-D2. Like in general, like it's about that big, it's about that shape. If you kind of have that in your mind, that's kind of what we're working with. All right. Okay. And then how we test it is, I mean, we throw it in the freezer. We put it in it's fancier than this, but it's an oven.
It's an oven, okay.
It's a box that gets hot and you control the temperature. That's an oven. We're not cooking food, we're cooking R2, but it's in there nonetheless. And so those are the tests that we're doing is hot and cold. And then sometimes, honestly, we stick it in a plane and we fly it way up in the air and we see what it does up there too. Because you can't replicate a real life scenario.
Oh, sure.
That's the best way to do it, right? Like, you don't know if you're going to jump out of that plane with a parachute until you go up and do it.
I remember I got a fly fishing pole when I was about 8 years old for Christmas. And in Southwest Kansas, that's probably the worst place to own a fly fishing pole. But I remember it said, no, you can practice, in your front yard, and you're practicing casting. And then we went to a creek in Colorado that spring. It's a lot different when you're actually standing in front of the water with it as opposed to, throwing it down your driveway.
Exactly.
So real world testing is, of course, important.
Yeah.
Are there standards that guide, what you're doing?
There are. So I'm opening my list here of some of the standards we use. So because we're a military contractor, we always start with Military Handbook 217.
Okay.
Long, deep, rich history of this handbook. Started in the 50s up in the Schenectady, Albany, New York area, and they're trying to set a standard and say, okay, a resistor that's 5 ohms, we're saying will always last within this many hours, 2 million hours, 3 million hours. This type of motor, this type of gear at this size will always last this amount of time if you ran.
Is there a factor of safety, I guess, that they built
into
that?
They built it in. And you got to think this is the late 40s, the early 1950s, right? So they're doing it by hand, but I mean, they are literally testing all of them and counting and putting the stopwatch to it and recording it. So it's been a few years since the 1950s. We've updated that handbook a number of times, but and there's another update coming soon, is what I've been told, but it's not been very thoroughly updated in a couple of decades. It's still considered the standard because it's the military handbook, but it doesn't account for a lot of the subtle advances that we get nowadays, right? It's like saying like I have an iPhone 14. It's a lot different than an iPhone 6, but both of them are way more advanced than the phone you and I grew up with at our mom and dad's house.
That's kind of where my mind would go with that as well, is saying, okay, well, maybe the standard hasn't updated, but you feel like those values would still be somewhat reasonable because, all right, maybe we've picked on resistors a lot. We're making resistors better than we did in the 40s.
Exactly.
So
we're making
if we're still
better.
using that standard, then the built-in factor safety should be more than adequate for today.
It should. And so then you run into Telcordia as an example. That's another standard where they said, hey, we're not in the military, we're in telecom. We are making these things better, right? We're running the different types of cable. We've got fiber optic. We've got T1 lines. That's not the same as phone cord and coax from 30, 40, 50 years ago.
Right.
And so they've upgraded their own. I'm not in the telecom industry. If I was, I'd probably use that standard, right? Yeah.
Sure.
And then there's another group that took the 217 data and they call it 217 plus, which I think it's great that they were able to like make it sound like a streaming service. I'd be a terrible channel, but it would be very useful at work. And so they took a lot of that same data and they applied those updates, both in understanding materials, understanding factors of safety, and being able to test a few more things. I mean, like there's literally stuff that exists today that didn't back then, right? In terms of like how we use LEDs or how small you can get capacitors and that sort of component. So yeah, there's a lot of that they build in and they look at. You tabulate it, you reference it, but then again, you have some number and it is what it is. And then you go and you test it. You throw it in the field. You heat it up. You cool it down. You put it up in the air. We see what it actually does. And that's how you feel good about what I send to you down the road.
I want to take a second to talk about Reliable Plant Conference. This is actually our 25th Reliable Plant Conference. It is going to be held at the Caribe Royale Resort in Orlando, Florida, July 31st through August 3rd. Please come and join us for workshops, speaker sessions, keynotes. We have an exhibit hall with over 100 exhibitors in it to find the solutions that you need to improve your reliability program, your lubrication program, and to network with your peers. Learn from them. Understand what solutions they use to improve their program. Come and learn from industry experts, from thought leaders, from people that are innovating in their reliability programs. And we want to see you there. Remember, July 31st through August 3rd. And of course, you can go to conference.reliableplant.com for more information. Now, on the design side of things, so someone's already come up with, all right, we have a need for a camera system. Now, you're trying to make sure all of the controls, all of everything that can fit into whatever device that is, falls within these standards or devised within these standards, and your end user is going to be the military. I mean, are you working hand in hand with them saying, all right, what all features, what all benefit, what are you actually looking for? I mean, how does this go with the design aspect when we're talking about Department of Defense or anything else?
So they come up with a laundry list of, we think it could do this. We'd like it to do this. Sometimes it's realistic. Sometimes it's not. That goes back to testing too, because we're testing operational, like how it actually works as much as we are how long it can last. So yeah, they also decide things like you should be able to put it together off the back of the truck within this amount of time, right? Like if we ship you a new one and we need to get that thing out in the field, it should take you less than a day, less than 6 hours. I mean, they change per the program, right? But they come up with those kind of ideas too. So yes, they're listing out what they think it should do, how they think they should do it, and to an extent, it's up to us to figure out how to make it achieve those things. When we overachieve, we take credit, we brag, we charge more. I think that's where the $10,000 hammer comes from. Is that that company really made a good hammer, and they were proud to show it off. I can see how that came about now.
Now, you keep talking about testing and everything else. What role would you play necessarily, as it gets into real world applications? So something has now been in service for a while. Are you getting data back from those in the field in use?
So we're very blessed in my group. We have a fantastic team of field service representatives. They're going out and they're working daily with the boots on the ground and saying like, hey, it was a little sluggish. This thing didn't seem like it worked correctly. Okay, we're going to get that data, not live, but about as close to live as you can get get when we're not going out with the equipment into the field, right? It's just coming back to base. And then, they're uploading that, and we're talking about it as often as possible. Hey, it seems like that this piece of memory card failed. Hey, it seems like this wire always seems to short out. Hey, it doesn't want to turn, all the way this way. There's some kind of mechanical binding. What's up with that? And then we're recording that data, loading it up, and then doing fracas, which is what you do, right? When you've been given the equipment and you show up at the plant and it's 50 years old, you're still looking at the history of failure. It's just, for us, the failures are all kind of brand new. There is no pattern. It is literally the first time the thing broke that way. When we do get a second one, we're not happy. You're never happy that it broke, but then you're like, a pattern.
Data set. Yeah.
We can follow the data. We can make better decisions. And so we did. We had one that by the third time it had failed, we had named it. We had a whole new procedure written up, and we were like excited because now we know how to approach it. We know how to fix it. We know how to make it better. And I mean, that's what you're always wanting to do with your product, is you want to make it better. And so that was enjoyable as much as anything else.
Now I'm going to back up real quick. Fracas, failure reporting and corrective action system.
Yeah.
We speak in a lot of acronyms and military and everything else. I mean, I can only imagine.
Yeah. So much worse.
So, I want to pick your brain here.
Yeah.
So you've been in industry, let's say heavy industry, power generation, stuff like that. You've been in the Navy, which, I mean, industrial aspect of that, you're propelling the boat, power plant the boat, all that good stuff. So compare what you're doing now with something the size of R2-D2 compared to something the size of a power plant.
And that's why I bring up the electrical side of it so much, because like that's what's in there, right? It's like we took a bunch of circuits and just dumped them in a box and shook it up, and it froze up. Yeah, it's moving not as much. And so the movements that you're thinking of are so much smaller, and the space that you're working in is so much smaller. And I don't get to go and hang from a pipe to reach the motor to be able to listen to it. It's like it's confined in a much smaller area. So you're almost like looking in on it instead of like being a part of the system.
Sure.
When I'm out in a plant or when I'm out in an industrial setting, you almost feel like you're part of the process. Like you're like, I can see where I am on the diagram from the plant manual. It's flowing right here. It's about to, heat up. It's about to cool down. No, you're outside of it the whole time, and you're like, you're barely poking. So that part's different.
But how are they the
scope?
same?
And they're the same because it's still a system. We've got a flow diagram, right? It's mostly electrical, but we've also got a camera flow. We've got mirrors. That's a really cool thing. If anyone ever gets the chance and you go in like to any place that does camera, in the back of the building, they have a mirror lab where they're like trying to figure out exactly what angles you should do to be able to do lens focus and refraction. And so what they'll do is they've got like a big bay, much longer than any standard meeting room you'd be in, and they've just got mirrors posted all over, and they're shooting the laser back and forth, and they're just seeing like, oh, it got a little better, it got a little worse. Because then what they do is they take those same angles and everything, and they squish it all together and pack it into R2,
whatever size of box it needs to fit
exactly. And that's true of the camera on your phone. It's true of the camera that you might just go take a nice wedding photo or scenic photo of. They've all got the different lenses and mirrors and inner workings that was like that. So it's fun to see it exploded. So that's kind of how I think of it. It's like it's a plant in a box. They took all of the equipment that might normally be spread out, and you can kind of look around and see, they shoved it all into a thing. And so you still have the flow diagram. It's all the same. You can see how the signal goes. You can see how all the inputs and outputs come out. You just are much more outside of it instead of being a part of it.
I want to dwell with the mirror thing because I find that fascinating.
Yeah.
All right. I'm thinking about reliability. And I've got an 8-year-old. I'm not going to give a mirror to my 8-year-old, right?
No.
But you're strapping this mirror onto, planes, boats, car. I don't know. I think about the good old Hummer jumping sand dunes somewhere. So, I mean, if you're thinking in a reliability aspect, I mean, that's got to give you some level of nightmares. I mean, thinking about something that could be as fragile as that going into this system. Is this all, as you start to build it? I mean, that's a structural, I guess, component of it. But then you have to worry about how the mirror is actually constructed, all of those aspects, right?
Yeah. And I'm not on the, I don't know as much about how they pick the material to do it as much as on the receiving end. But we do make sure that it stows is the term we use.
Okay.
You can lock it up, right? It doesn't jiggle. We use different means to hold it in place and seal it in against the environment. So you're moving and you're going through a bad area. It's dusty, whatever. we're locked up. We're not worried about it hitting that. It's fine to take the bounce, so to speak. But yeah, I don't know how they pick that part.
The dirt, of course, is a killer in my environment. Right?
Always is.
We think about dirt getting in the oil and everything else. I mean, how are you guys counteracting?
Yeah, so we're partly counteracting it by making sure that it seals up really good. Doing the check on the seals is one of our basic maintenance tasks. Of okay, we're shut down, we're closed. Check the seals. Is the seal actually doing what it's supposed to, and locking the camera up? After that, we're putting it far enough above where dirt normally is that we're not as worried about it. To be frank, like it's just we get it so high up that there shouldn't be dirt. There should be rain. That's fine. We'll drive through the rain a little bit. Maybe we put a window over it. Maybe we don't. That kind of depends. But yeah, we're mostly focusing on keeping it out by making sure that it's tight. And then when it mechanically binds, that might be one of the things we look at, right? And because it's electrical, because there's the mirrors, now you can't just go in and like blow it out with compressed air,
Sure.
right? Yeah, that's how you damage stuff. So no, it's really about prevention of getting it in the first place. We were talking before we started recording that, sometimes we'll just open the bay doors where our program works and just point it across the tarmac and see stuff. Well, I mean, it's dusty out there too. It blows in. Sometimes that's what happens. Then you shut the door and then you take a minute and you kind of go over with your fine tooth comb, and then you make sure that it does the full range of motion before it shuts down. So
now, I know we're running low on time, but I've got just a couple more things. So the first one, if you do your job exceptionally well on the design front, does that mean that you're not going to have some sort of failure out there in the field?
I mean, failure is random, is what we always say,
Sure.
right? Life happens, stuff happens. It can be a lemon. We could miss it. I will say that we've not seen failures occur much earlier than what we said would happen.
So you are saying there is a finite point, right? Yeah, because you can't say, well, this is going to last into perpetuity, but it should last fault-free to this point.
Yes.
And that means job well done for what you've done.
Exactly. And then every time we redesign or we come up with a new aspect of what we think it should do next, that's kind of the first step. Okay, let's look at these components. If we change these components and we thought it did this, did it make it better or worse? It might make it worse, but if that improved the performance, that might be worth it. Obviously, most of the time you want it to last longer, and most of the changes that we've made do that. But we have one of the cameras in our system where it's not the best camera. It doesn't last the longest, but it performs to the exact specifications that we want. And so we said, you know what? It's fine. We don't need to try and make it last longer and risk losing the picture that we're trying to see. And so we'll just let it stay in there.
That's
for a
decision
bit longer.
that has to be made.
Exactly. Yeah. So it's not just throwing it out there and saying like it failed or it didn't fail in terms of like it stayed on, right? We're defining failure as part of our approach to it. And so that's part of it too, is that we have more than one camera in the camera system. So, hey, you know what? We go through and most of them work. That might be considered a success. It depends on which camera turned off. So, that I think that goes back to a lot of how people misunderstand failure in the first place. Is failure is not binary, right? When we say it starts to fail, if it degrades a certain amount, that's a failure, right?
Sure.
It didn't have to turn all the way off. And so it's kind of thinking of that same aspect of like defining it, listing out exactly what it means in the mission, in the operation, in productivity, right? If your plant is still pumping out the amount of widgets or chemicals that you need to make or electrons, like we're good. It's not a failure, right? It's running a little slow. We got to be thinking about that. We got to put some maintenance plans together.
It's that whole minimum level of performance that we define.
Exactly. And so we have that too, even from a design and thinking of it from a design standpoint. It's like, great, we think the hours we designed it to last meets what the customer wants. And then we go out in the field and it seems like it mostly does. All right.
No, that's great. So last question here. Is there anything that you would want to put out there, kind of a message, either maybe people that are looking to get into reliability, or maybe it is those people that are saying, if they would just design it better, we wouldn't have these problems. So kind of last little pitch to you here.
No, absolutely. I'm amazed at how much it's the same, but how much it's different, right? Again, we're doing a lot of the same processes. We're doing FMEA, failure modes effects analysis. We're doing fracas that we talked about, but we're the ones who get to originally consider the design. And so when we're selling it, we're sending it off. It's like we did put in a lot of thought. Like we did it the best we could. But like I'm thinking of it, it's 2023. The thing that we're selling and using is supposed to still be working 20 years from now. Right. I don't know what technology is going to change in 20 years. I can only tell you that today we made the best decision we could. And so that makes me reflect back on, any time that a motor broke and you probably had an unkind name for the motor in your plant that broke all the time. And you're like, why would they do it this way? It's like, that might have been literally the best that could be done at the time with what they knew and how they checked it. So it's like always be open to new ways to evaluate it. But when you're looking back and thinking like how it got put together, you got to kind of understand where it came from. We're using a handbook from 70 years ago. That's kind of the mindset.
Updates coming soon, though.
It is. I've been promised at a conference earlier this year that they were soon to release.
That's great. Dan, I really appreciate you stopping by. This has been a great conversation. I hope that you'll come back because I want to pick your brain on some other topics as well.
Would love to. I know we didn't get into the conspiracy theory about what you do with the camera.
Yeah, not yet, right?
We'll get there.
All right. And I want to thank you guys for watching another episode of the podcast. Of course, it's available anywhere that you get your podcast. If you have any questions, comments, topics that you'd like us to cover, you can email us at podcast@noria.com. And of course, thank you once again for your patience here.